Can the sine function be factored? Well, it turns out that yes, it can. In fact, the very famous mathematician Euler essentially became famous. He sort of shot to international stardom because he found a way to factor sine. And really, it was what he did with his factorization, which was to solve the so-called Basel problem. Now, the Basel problem was the problem of finding the sum of this series. And notice here that the denominators are the perfect squares, 4, 9, 16, 25, and so forth. If we start adding these numbers up, and you can actually do this on a calculator, so 1 plus 1/4, that'd be 1.25, and then add 1/9, 1/16, and so on. Well, this starts getting closer and closer to, starts converging to some number here. And mathematicians in Euler's day had calculated this number to several decimal places, about the number that I've shown right here. But they were completely stumped as to what the number is. And this was known as the Basel problem, to try to figure out what this number is. Oh, and Basel, by the way, is the name of a city in Switzerland where many mathematicians at the time were based, including Euler himself. Well, Euler showed what this number is. It turns out that it's pi squared over 6, amazingly, but he was able to show this using his sine factorization. And we'll see this in a minute. And another really cool thing that just follows immediately from the sine factorization is this. This is called the Wallis product. This says if you take 2 over 1 and multiply by 2 over 3, then multiply by 4 over 3, and notice the pattern here. We have 2, 2, 4, 4, 6, 6, 8, 8 in the numerator, and 1, 3, 3, 5, 5, 7, 7 in the denominator. If you keep multiplying, this is going to get closer and closer to, it's going to converge to pi over 2. I mean, that's incredible. Now, this formula was known in Euler's time, but it ends up falling just right away from how he factored sine. So what was Euler's insight into factoring sine? How did he do it? Well, here we have the so-called power series expansion for sine of x. And this will be familiar to you if you've had a second or third semester of calculus. But this is really an incredible formula. In fact, I remember in high school, I ran across this formula in an Encyclopedia Britannica. You know, like the physical book. This is before Wikipedia. And I was just mesmerized by it. Like, what the heck in the world is this? I mean, I'm so used to thinking of sine in terms of opposite of our hypotenuse or the unit circle. This just seems crazy. Well, I'll give you a visual demonstration of what this formula is all about in a minute. But Euler knew the formula, this power series. In fact, it goes all the way back to Isaac Newton, believe it or not. But Euler sort of thought of this power series as being almost like an infinite degree polynomial. Now, it's not a polynomial, of course. Polynomials can't have infinite degree. But he reasoned that if we can factor polynomials based on their roots, their zeros, maybe we can do the same thing with sine, since we know what the zeros of sine are. Now, our first thought might be, well, since the zeros of sine are the multiples of pi, well, let's factor sine like this. Sine of x is x times x minus pi times x plus pi times x minus 2 pi times x plus 2 pi, and so on. But there's a real problem with this approach. And Euler knew about this problem and he had to fix it. So what's the issue? Well, if we let f of x be defined by x times x minus pi times x plus pi, and so on, and if we just plug in a number for x, so it can really be any number other than a multiple of pi. Let's just take 5. So what is f of 5? Well, notice when we plug it in sort of way out here, if we do, say, 5 plus 3 pi, well, then notice we'll get a pretty big positive number. And if we were to do 5 minus 3 pi, we get a fairly big negative number. And if we go further to the right, we're just going to get even bigger numbers. So if we were to kind of multiply this out factor by factor, it's just going to start swinging around wildly. So it definitely won't converge. And the same thing will happen really for any number that's not a multiple of pi. So this has no hope of working. But what's the problem? Well, if we do an infinite product, we just multiply infinitely many numbers, what we'd like to have happen in order for the product to converge is to have the numbers kind of settle down and get closer and closer to 1. So just like for an infinite series, when we're adding infinitely many numbers, in order for the series to converge, the numbers, the terms, have to get closer and closer to 0. Well, for products, we want the numbers to approach 1. And I'll show you an elegant little theorem about this in a bit. But remember that 0 is the additive identity. If you add 0 to anything, it stays the same. And if you add a number that's close to 0, it only changes a little bit. Well, 1 is the multiplicative identity. If you multiply something by 1, it stays the same. And if you multiply by something close to 1, it only changes a little. So that's essentially why we want these numbers to get close to 1. So how did Euler fix this problem? Well, if we take a polynomial, let's just take x squared minus 7x plus 10. And if we factor this, notice it factors to be x minus 5 times x minus 2. And normally we would just sort of stop here. We're done. We factored it. Well, what if we take this a step further and take out a negative 5 out of this factor? And write this as negative 5 times negative x over 5 plus 1. And notice if you distribute the negative 5 here, you just get this. And we can do the same thing over here with negative 2. If we distribute this negative 2, we get this. And we can ultimately take it a step further and do the negative 2 times negative 5. We get this 10 out front. And we can rewrite this factor like this, 1 minus x over 5. And we can rewrite this factor like this. So notice this is another way to factor this polynomial. We have a different coefficient out front and the factors look different, but notice that the x minus 5 factor sort of corresponds to the 1 minus x over 5 factor, right? In both cases, if you plug in 5 for x, you get 0. And same thing here, the x minus 2 corresponds to this factor. So what Euler realized is that we need to have factors that look like this, because notice how the 1 stands out here. And 1 is going to be important for our infinite product. So here is the correct approach, the one that Euler ultimately ended up using. So what we do is we write sine of x as x times not x minus pi, but 1 minus x over pi. And then not x plus pi, but 1 plus x over pi, and so on. And notice, by the way, if we plug in a number like 5 this time, well, the factors are going to be getting closer and closer to 1. In fact, they'll be getting close to 1 sufficiently fast in order for this product to converge. And then we get some simplification. We can multiply these two factors, for example, to get this. And same thing here, multiply these and you get this, and so on. And we can write the whole thing more compactly like this. This is the notation for product. So just like sigma means sum, this means product. We keep the x out front here, but notice the factors all have the same form. 1 minus x squared over some constant times pi squared. So here the constant is 1, then 4, then 9. It's really the perfect squares. And notice here that when n is 1, we get this factor. When n is 2, we get this factor. When n is 3, we get this one, and so on. And I've typed it here in bigger font, but here's the question. How did Euler know that this was the correct way to factor sine? Now, we know that this factorization would have the correct zeros, and we can show that it converges, but there are lots of functions that have the same zeros as the sine function. For example, how do we know we aren't supposed to have some coefficient out front here? Or even some function, so a function that doesn't have any zeros, like an e to the x out here. Well, Euler's intuition about this turned out to be correct, and he came up with very strong evidence and arguments that this does converge to sine, which I'll explain. But it wasn't until more than 100 years later that it was proved rigorously that this product actually does converge to sine. And at the end of the video, I'll talk more about that rigorous proof. But let's first look at some graphs in Desmos. Now, I've graphed the sine function here, and as promised, I want to first look at the power series for sine, and then we'll look at the product. Well, if we wanted to find a linear approximation of the sine function at x equals 0, the best linear approximation is just y equals x. Notice that it goes through 0, 0, just like sine does, and it has the same slope as sine. The graphs just kind of hug each other near 0. Well, if we wanted to do a quadratic approximation at 0, it turns out that we can't do any better than just y equals x. But the best cubic approximation is x minus x cubed over 3 factorial. So really just x minus x cubed over 6. And where this comes from, if you know calculus, is by finding the cubic polynomial that goes through 0, 0 and has the same first 3 derivatives as the sine function at 0. And we can't do any better than this with a 4th degree polynomial, but if we move up to 5th degree, we get this. And continuing on, notice that what we're getting here is really the power series for sine of x. This is really just where the power series comes from. But amazingly, this is getting closer and closer to the sine function, not only near 0, where we might expect it to, because we're approximating sine at 0, but also farther and farther out here. In fact, the power series just converges exactly to the sine function for all values of x. And this is a really remarkable property of the sine function, that by knowing how sine behaves at 0, that completely determines how it behaves everywhere else. And this has to do with the fact that sine is a so-called analytic function. And analytic functions are what you study in complex analysis. But that's what the power series for sine is all about. Okay, now what about the product factorization? Well, let's first look at how the incorrect method that we looked at fails. Now, here's just y equals x again, and now y equals x times x minus pi. And remember, this was the incorrect kind of factor, x minus pi. And notice that doesn't do a good job at all. Maybe if we flip it upside down, take a negative, it's still not very good. Then notice this is even worse. And keep going, this is looking terrible. In fact, these almost look like vertical lines. They're not, it's a polynomial. But for example, at x equals 5, for one of these, it would be way, way up high. And then you go to the next one, it'd be way, way down there. So clearly, this just doesn't work. In fact, the only values it really works for are the multiples of pi, the zeros. Now, what about Euler's way? Well, notice that we start out with x again, and if we add another factor, we get a reasonably good approximation. It has x-intercepts, or zeros, at 0 and at pi and negative pi, and it's a somewhat good approximation in here. If we do another factor, well, we get these 5 zeros correct, and it's a pretty good approximation in here, and well, not quite as good out here, but let's keep going. Okay, now I'll have to zoom out and keep going. And it's just satisfying to watch, right? Like a zipper on a jacket that just perfectly glides up on the first try, no snags, no misalignment. And so this is pretty strong evidence that we have the correct factorization. Although Euler himself didn't have Desmos or any graphing calculator, so he had a different kind of evidence, which I'll now show you. Now, people often take our product expansion and divide both sides by x. So we rewrite it like this. Now, we're going to take this and plug in pi over 2 for x on both sides and see what happens. Okay, so here's our product, and we're going to plug in pi over 2 here, here, and here. So let x equal pi over 2. The left side, we have sine of pi over 2 over pi over 2 equals this product, and we plug in pi over 2 right here for x as well. Now, sine of pi over 2 is just 1, so the left-hand side is just 1 over pi over 2, which is really just 2 over pi. And then on the right-hand side, we have pi over 2 squared. That's just pi squared over 4. This pi squared and that pi squared will cancel, and we just end up getting 1 minus 1 over 4n squared. And then we can get a common denominator, so just rewrite 1 as 4n squared over 4n squared, write it like this, then factor the numerator to be 2n minus 1 times 2n plus 1, and factor the denominator is just 2n times 2n. And then we can just start plugging in numbers for n. So when we plug in n equals 1, notice we get this, 1 times 3 over 2 times 2. When we plug in 2, we get this, 3 times 5 over 4 times 4, and so on. So notice what we end up with is 2 over pi equals this product. And if we take the reciprocal of both sides, we'll have the Wallis product. Pi over 2 equals the reciprocal of this. Okay, so taking reciprocal of both sides and getting rid of the parentheses, we have pi over 2 equals this. So this beautiful little identity drops right out of our product formula for sine. But it's actually pretty good confirmation that Euler had found the correct factorization of sine, because this identity was already known. So the fact that his purported factorization of sine gives the correct value for this product is strong evidence that his factorization of sine was right. And even stronger evidence was provided by his solution of the Basel problem. And remember, the Basel problem was to try to figure out what this number is here. Now, I don't think it's too much of a stretch to say that what Euler did here, and what we've seen so far and what we're about to see especially, is some of the most beautiful math there is. It's almost like he's painting the Mona Lisa of mathematics. Okay, so what did he do? Well, we're going to start with our product expansion for sine of x, and actually we're going to divide both sides by x again. So we have sine of x over x equals this, and we're going to treat the left and right-hand sides separately. So we'll begin with the left-hand side, sine of x over x. Well, we can rewrite that as 1 over x times sine of x, and this is the power series for sine of x. And then we just distribute the 1 over x here, so basically lower all these by 1, and we get this. So this is the power series, really, for sine of x over x, the left-hand side. Now what we're going to do next is take the right-hand side, this infinite product, and formally expand it. And when I say formally, what I mean is that we're not going to worry about convergence issues. And we're going to expand it kind of like how you'd expand a product of polynomials. So basically just multiplying it out term by term. So taking one term here from each factor. So either the one or the quadratic term. And when we multiply this out, there's no way to get a linear term, a degree 1 term, because every factor contains only degree 0 or degree 2. Now, we can get a constant, right? The constant 1 just by doing 1 times 1 times 1 times 1. So we end up with a 1 here, but notice that we'll have a plus 0x. Now, what about x squared terms? Well, we can get x squared terms from choosing a single quadratic term from one factor. So like this negative x squared over 4 pi squared, and multiplying it with 1s from all the other factors. So we do 1 times this times 1 times 1 times 1 and so on. And that's the only way to get a quadratic term. If you were to ever multiply 2 of these like x squared terms, then you'll have something that's at least a degree 4 term. So what we end up with is this. We have 1 plus 0x plus this, all of this here, these are x squared terms, plus 0x cubed. So notice we can't get any x cubed terms, degree 3 terms. And you will have degree 4 terms. It's a little trickier to come up with what the degree 4 terms would look like. But this is what we have. And then notice in the next step, what we can do is factor out this x squared and factor out the minus 1 over pi. And notice what we have left here. Now, if we go back here, the left-hand side of this equation has a power series expansion. The coefficient of x squared in that expansion is negative 1 over 3 factorial, or in other words, negative 1/6. Well, the right-hand side also expands into a power series, and the coefficient of x squared in that power series is this. And since the power series expansion for a function, if it exists, it has to be unique, we should have that this should equal negative 1/6. Okay, so that's what I've written here. This equals negative 1/6. But then if you just multiply both sides by negative pi squared, what you end up with is this. And this is the solution of the Basel problem. 1 plus 1/4 plus 1/9 plus 1/16 plus 1 over 25 and so forth. That converges to pi squared over 6. Now, this was also very strong confirmation that Euler's sine factorization was correct because nobody knew what this was going to be, but they had calculated it out to quite a few decimal places. And when Euler used his sine factorization to figure out that this should equal this, and he calculated this to a bunch of decimal places, it ended up being correct to as many decimal places as they could calculate. I do want to mention here, since we've been talking about infinite products, and they tend to not be as well known as infinite series, that there's an elegant theorem that relates infinite products to infinite series. The theorem says that this product will converge, where we've written the terms in this form. This product will converge if and only if this series converges. In other words, the exact rate at which these ANs need to approach 0 in order for this series to converge is the exact rate at which these factors need to approach 1 in order for the product to converge. I mean, that's a great little result that's not immediately obvious, but you can prove it using logarithms. But I think this is a great little result that's not as well known as it should be. Now, Euler published his Basel solution in 1740, and this really shocked the world of mathematics, but he didn't actually publish a formal treatment of the sine product until a few years later. And it wasn't until more than 100 years later that Weierstrass and Hadamard fully and rigorously verified the sine factorization. So what Weierstrass did was to provide a general framework for writing entire functions as infinite products over their zeros, the so-called Weierstrass factorization theorem. And entire functions, by the way, are just functions that are differentiable in a complex sense on the entire complex plane. Okay, they're analytic on the whole plane. And Hadamard developed a growth theory of entire functions, where you talk about the so-called order and type of an entire function. And this allowed Euler's sine factorization to finally be verified. But really understanding all the details would require a significant amount of complex analysis. But thank you for watching and have a wonderful day.